So this video is a follow-up video on friction, and I'm specifically wanting to just have a brief discussion on kinetic friction versus static friction, and also quickly look at the equation and a couple of applications. So I recommend this is the video following the notes video with the definitions of these and some very basic examples. And so we want to think about kinetic friction versus static friction. And I just want to point out that the vast majority of the time, static friction is greater than kinetic friction. Now this has to do with it being locked in place. There's certainly some scenarios, maybe where things are getting hot, maybe there's some kind of other things at play. But for all practical purposes, we want to think that static friction is normally more than kinetic friction. And so, as I already mentioned, a couple applications of this is just from a safety standpoint. It's worth knowing if you start sliding, that static friction before you start sliding is normally greater. So the force that's keeping you on a hillside or perhaps a roof or some other scenario, whatever that force is, once it converts from static to sliding, and immediately you lose a lot of friction, and so you can have a tendency to fall. You can think about in a tug of war or something like that. Once somebody's feet start to slide, they're pretty much done. Some other examples that we could see of this would be with anti-lock brakes and basically the exact same thing with tires spinning in a car. When you're driving in a car, although yes, your tires are rolling along, it's worth noting that the friction force that is pushing you along from those tires, there's a friction force. Your tires are trying to rotate. This would, of course, be in an all-wheel drive vehicle. If those tires are rotating this direction, there's a friction force. If your tires are not spinning, you're actually dealing with a situation where it's static friction is the force that's pushing your car forwards. Now, the opposite is true when you slam on your brakes, or you just hit your brakes and your tires start resisting the rolling and start trying to slow down in this direction. There could be a force put this way on your car. Sorry, there's a force of friction this way on the ground, which Newton's third law, there's a force this way placed on the tire that would cause your car to have an unbalanced force that way, which would cause you to slow down. These forces, when tires are rolling normal, they are static friction because the tire isn't spinning. When the tire starts spinning or skidding, either one, if you're braking or gassing it, you're dealing with kinetic friction where the tire is actually moving relative and sliding across the surface of this. And so what anti-lock brakes do is they actually put the most resistance of rolling on your tire. They make it slow down as much as possible, but as soon as you start to skid, that tire immediately lets up and starts to roll a little bit, so it locks back in place. So if you've ever felt anti-lock brakes, it feels like a kind of like a da-da-da-da-da-da-da. What you're feeling is the brakes are engaging, trying to slow it down, and as soon as it starts to skid, they start to roll again. And so anti-lock brakes are an absolute miracle that we have that leverages the fact that static friction is greater than kinetic friction. It has saved countless lives, and they're very, very effective at stopping cars. I also wanted to follow up with this equation. We've already discussed it before, but it's worth noting that the equation to quantify the force of friction is this force normal times mu. Mu is the coefficient of friction, and mu has to do with those two types of materials that are interacting. How much are they locking in together? Depending on how they interact, that has to do with the materials, and this has to do with how heavy the object is and that force of gravity on it, which is normally equal to the force normal. So what's the interesting point about this is, if we were to think about this block of wood, and it has this surface right here is kind of like a felt, and this is the exact same surface. What we would find is then if you pulled this felt across here, the friction that this block would experience with it laying this way would actually be identical to the friction it would experience with it lying this way. Now this is not something I think that's intuitive to a lot of people, but if you look at the equation, this is going to be a product of this material, this surface in the paper, mu, And then the force normal is a product of the force of gravity on this. So the force of friction would be the same here versus here. Now what if we put it this way? Well, now actually it could be different because we're dealing with the different mu. Because now we're dealing with the coefficient of friction between this surface and the paper. So while this friction might be different than this friction, if the surfaces are the same, it actually doesn't matter the amount of area that's under it. And so that's another thing that's not always intuitive, I think. And there are certainly exceptions. For example, if you're pulling something that's like really, really narrow and it's digging into the material, you get more involved than just friction. But typically speaking, what I've just said works. Thank you. Have a great day.